Hello everyone, welcome to the ninth lecture of the course Mathematical Modeling and Simulation. In this lecture, we will see how to derive a simple prey-predator model and linear relationship model and draw the interpretation of its output. If I talk about the first prey-predator model, it was developed by Vito Volterra, and he was a famous Italian mathematician who retired from a distinguished career in pure mathematics in early 1920s. His son-in-law, whose name was Humberto, he was a biologist who studied the populations of various species of fish in Adriatic Sea. In 1926, Ancona completed statistical studies on the numbers of each species sold on the fish market of the three ports Fiume, Trieste and Venice. The percentage of the predator species shark, stake, rays, etc. in the Fiume catch are shown in the following table. So this is the year and these are the percentage. Now he observed that the highest percentage of predator occurred during and just after the World War, when fishing was drastically curtailed. He concluded that the prey-predator balance was at its natural state during the war, and that the intense fishing before and after the World War disturbed this natural balance to detriment of predators. Now, Ancona asked Volterra if he could come up with some mathematical model and explain what's going on. So after a few months, Volterra developed a series of models for the interaction of two or more species. So the first and the simplest of these models will be discussed in this lecture, and also there was another person, Alfred Lotka, and he was an American mathematical biologist who also formulated the same model as Volterra independently and about the same time. So the name is written as Lotka Volterra because it was developed by both of these, but both of them did it independently without knowing each other. Now for formulating the prey-predator model, it is obvious that we should make some assumptions, then only we can make a or formulate a prey-predator model. So what is the first assumption? That suppose that in a closed ecosystem there are only two types of animal, that are the prey and the predator. This is the first assumption. Then they form a simple food chain where the predator species hunts the prey species, and the prey species, they depend on the vegetation, and the predator species is totally dependent on the prey species for its food supply, and prey species has unlimited food supply and has no threat to its growth other than the predator. And this size of two population can be described by a simple two nonlinear first order differential equation. So let us go step by step that how to develop a model. So according to the fourth assumption, we have seen that if there is no predator, then the prey species will grow exponentially. Now if xt denotes the prey population, then we can write dx by dt is equal to ax in the absence of the predator, because if there is no predator then the prey will grow exponentially. But we know that there are predators and we denote the population by y. So if predator eats the prey, there should be a negative component in the prey growth rate, and obviously that will be proportional to the product of the population sizes. So we can write the complete equation for the prey population as this. This is the predation rate, this is the growth rate, and here you can see that if there is no predator, it is growing exponentially, and in the presence of predator they encounter prey, right? They encounter the prey which is proportional to the sizes of the two population, and obviously this encounter will lead to the death of the prey, and so there is a negative sign, and obviously the negative component of the growth rate is proportional to the product of x and y. So this is the equation for the prey population. Now we will see the equation of the predator population. So now if you consider that there is no food supply, this means that there is no prey population, then it will die out, because as our assumption says that it depends only upon the prey population for its survival. So it will decay exponentially. This shows that the predator population will decay exponentially in the absence of prey. But we have the food supply, the prey, and what's bad for the prey is good for the predator. So we can have our differential equation as this. This means that the component which was getting minus from the previous equation is now adding up over here, because as predator eats prey, it will get the energy to support the growth of the predator population, and this is proportional to the component that is getting minus from the prey component, and obviously some energy is lost, so alpha is converted into gamma, and gamma will be less than alpha if you talk about the relationship between the parameter. Now we are interested in doing the mathematical analysis for this model. So I have told you that xt denotes the prey population and yt denotes the predator population. Then this was the model, and if you see these parameters all are positive constant. Now obviously I have told you this, that if there is no predator it will grow exponentially, and if there is no prey it will decay exponentially. So if you solve this system, or if you find out the equilibrium point, how you can find out the equilibrium point? Equilibrium point can be found out by putting them equal to 0. So if you solve this, you can see that you will get two equilibrium point, that is this and this. So I have used this simple Mathematica code. You can write this in Mathematica and you can get this equilibrium point easily, or you can solve by hand also. This one is useful for the complicated system. Now if you find out the Jacobian matrix, the Jacobian matrix is this. So I have told you how to find out the Jacobian matrix. So if you remember, you can find out easily the Jacobian matrix. This is not about any point, this is a general Jacobian matrix. Now if I take my point 0 0, that is one of my equilibrium point, my Jacobian matrix will become this. Now what are the eigenvalues? You can see, easily calculate the eigenvalues are a and minus c. Since this one is positive, this will be an unstable node. So here I have drawn the vector plot for this system of differential equation. This can be again made by utilizing this Mathematica code. You can write this. This one is the differential equation you have to put, and you can keep this parameter values as this given over here, and this is the range. Other things you can leave as it is, and you can generate the figure for the vector plots for the given differential equation. Now if you see, this one is my 0, 0 point, and since this was a saddle point, see one side, the one of the eigenvalues was negative, so you can see that this side it is approaching towards the 0 0 equilibrium point, but from the other side it is going away. Now we are going to analyze the next equilibrium point. So you can see that we have got our next equilibrium point as this, and the Jacobian matrix, if we take out the Jacobian matrix by putting this as in the place of x and y, you will get this matrix. Now if you find out the eigenvalue, you can see that you are getting the eigenvalues as this. So this one is a stable center. Now I have told you that if we have 0 real part, we cannot tell anything about the linearization, but here we have found out that it is a stable center, and you can see that this one is my other equilibrium point, that is C by gamma and A by alpha. This is C by gamma and A by alpha. Obviously this C and A is given over here. So you can see that if you put C by gamma, this is 1, and A by alpha, this is coming out to be 2. So this is 1 comma 2, and you can see that this one is a stable spiral. So since it was a complex eigenvalue, but the real part was coming out to be 0, with the linear analysis we cannot say anything, but we found out that this was a stable spiral by this plot. And this you can see that all the solution in the neighborhood of this equilibrium point are trying to converge to this point. So this one is a stable center. Now if we draw plot in the MATLAB, which I have already shown in the video for the MATLAB code, you can use that code, and you can see that if you plot the graph between the time and the population density, you can see that there is an oscillatory behavior that is observed for the prey-predator dynamics. You can see that over here the prey population is maximum, and since the predator population is getting enough food, it is also growing to its maximum value. And due to this predator is growing to maximum, it will eat more prey, and then you can see that the prey population, this blue one is for prey, this is going approximately to 0, and then the predator population, which depends entirely upon the prey population, will begin to starve, and it will also go down. And as the predator population goes down, now prey population will get a better chance to live now, and then it will again show a uprise, and this thing will happen again and again. So this can be also seen by the phase portrait diagram between the prey and predator. You can see that when prey is high, the predator keeps on increasing, and then the prey population goes to 0, and this continues, this dynamic continues in the cycle. Here I have shown that what parameters I have set in my MATLAB code, and this one is the initial condition what I have used for plotting these figures. Now if we talk about the two population model, we can classify this as competitive, cooperative, and prey predator. We can always use this dx by dt for the prey population and dy by dt for the predator population, and then with the sign we can tell that whether it is cooperative, competitive, or prey predator. So let me show you all these models. So here you can see that the plus sign is there, so this one is a cooperative model. Now if there is a negative sign in both, then that means that this one is competitive model, and if one is negative and one is positive, then this is a prey predator model. So this model I have already discussed, but if you see other type of, you can easily classify that between the competitive and cooperative. Now I want to show you one more complex model. So this one is for the ecosystem containing the 3 species. So what are the 3 species? Let X be the grass grazer whose population is in isolation, and they obey the logistic equation, and they are preyed by the species Y, who in turn is a sole source of species Z. Like X is eaten by Y and Y is eaten by Z, and X grows logistically. So if you want to model this, your differential equation will look like this. This is for the logistic, and you can see that here since Y eats this X, so this is the negative component. When they both interact, Y will eat X, and there is a negative component which will go in plus to this Y population, and obviously it depends on X, so there is negative. That means that in the absence of X, it will decay exponentially. Now again this y population is eaten by this z population. So here when there is an interaction between, it will eat it and then it will be transferred into this equation, because what is harmful for this y is beneficial for z. The energy will be converted over here, and this is showing that it will decay exponentially in the absence of the prey population y. So you can increase the complexity of your prey predator model depending upon the real scenario and the species you want to model. Now we will discuss an interesting model that are relationship models. So we will first describe a simple model of love affairs which was given by Strogatz in 1988. So this RT represents the Romeo's love or hate for the Juliet at any time t, and this JT represents the Juliet's love or hate for Romeo at any time t. Now in the first simple model we will see that the Romeo's love to the Juliet, that is this dr by dt, is proportional to her love for him, and Juliet's love derivative towards Romeo is proportional to his love for her. So if we write this in a mathematical equation, we will have this mathematical model. So you can understand that this one is giving you the rate of Romeo's love and this is rate of Juliet's love. So this one I have taken from this article. So you can refer this article also if you want to read more. Now our task is to solve this differential equation and get an interpretation of what is happening in their relationship. So I used this code. Obviously you can solve it by your hand also, but since we also want to do the simulation, I have used this code in Mathematica to solve this differential equation, and you can see that I am getting the solution as this. So Romeo's love is also hyperbolic and the Juliet's love is also hyperbolic, that means exponential. So if I draw the graph of this, you can see that the love intensity is rising day by day. You can easily see that as the time is increasing, their love intensity is also increasing with time. And you can see over here, this is a phase portrait. This is showing exactly the same thing, that their love is growing linearly. Now we will see another interesting relationship model, that is a trigonometric love model according to Steven Strogatz. As we have seen in the previous case that the love was hyperbolic, but in reality not all the love stories proceed hyperbolically in time. Unfortunately, as we have seen in both literature and experience, love doesn't grow exponentially. So Strogatz has its own version of Romeo and Juliet, and he described Romeo as a fickle lover. So what is this fickle lover? This means that more Juliet loves him, more he runs away and hide. But when Juliet gets discouraged and back off due to this behavior, Romeo begins to find her strangely attractive. So that's why he is called as fickle lover. But on other hand, if we talk about the Juliet's feeling, she warms up when he loves her and she grows cold when he does not. So the differential equation for this case will become as this. You can see this negative sign represents that Romeo is a fickle lover. Now if you want to solve this set of differential equation, it's very simple. If you see the first equation, I can write dr by dt is equal to minus aj. Now if I differentiate this again, I will get what? I will get minus a dj by dt. Now if I put this, because here dj by dt is already given, so if I put over here, I can get the differential equation as plus abr, which is a linear second order differential equation. Now if you put a is equal to 3 and b is equal to 5, and then you can solve the, like, find the auxiliary equation, you will get like this, right? You have already done this in your differential equation class, that how you can solve the second order differential equation. So this is the auxiliary equation, and you can see that you will get the roots of this auxiliary equation as this. Now if you put the initial condition as, like, at time t is equal to 0, the Romeo's intensity of the love was 1 and Juliet was 0, you will see that you are getting the solution as this. Now you can ask one question, that what is the percentage of time when both Romeo and Juliet love each other? So this is an interesting question which you can ask, and that means that the love intensity for both of them is greater than 0. So what we do, this is our solution, and if you square and if you add them, you will get the equation like this, and this represents an equation of ellipse. Now if you will draw the graph of this ellipse, you will find that at 1/4 Romeo and Juliet are in love, in 1/4 they hate each other, and the rest of the time one loves and the other hate. I will show you the figure also. This is an article where you can find the modeling of this kind of differential equation. It was developed in 1988 by Stephen Strogatz. So this one is the phase portrait, which I have told you will be the equation of the ellipse, and if you draw it, like if you do 4 parts, this is part 1, part 2, part 3 and part 4. Here you can see that in part 2 both have the love intensity as positive, so here only both will love each other. Here you can see that Romeo has a positive feeling but Juliet has negative feeling. Here both of them have negative feeling, right? Here one is loving and one is hating. Here also you can see that Romeo is hating and Juliet is loving, so only this portion they both love each other. So this is the interpretation what you get from solving your differential equation, and you can see that how strong the differential equations are. And if you draw the time series, you can see the same thing, that the love and the hate is happening periodically, that one time they both love and the other time they hate each other. Now I will end with showing this mathematical model which was given by these two authors. If you are interested, you can go and do the mathematical analysis and numerical simulation for this model. I will also encourage you to draw your own relationship models or prey-predator model after watching this video, and draw the physical interpretation for it. And please let me know what are the interesting results you come up with. So I will end this lecture over here. Thank you.